Hello everyone, welcome back to Technologies Discussion Channel. For this video, I'd like to continue the discussion on filter design. In fact, there are two very popular ways to design filter. The first method will be using this image parameter to design filter, typically for low pass and high pass filter. Another method will be the insertion loss method. This is like using the Chebyshev, using the Butterworth method to design filter design, which is widely adopted now. But this video, okay, I'm going to concentrate on this method, which is the image parameter. Okay, so we are going to make use of constant K and m-Derived filter session to design a low pass filter. So later on, I have a working example to design a low pass filter using this method, image parameter, to design this low pass filter. So this will be the objective of this video. Guys, this is my email. If you have any question regards on this discussion, please drop me an email. Okay? Or if not, I actually prefer you guys to ask me your question through the comment. Let's start. The image parameters method of filter design typically involve the specification of a passband and also the spot band characteristics for a cascade of simple two-port network. So basically this diagram here show a two-port network, input and output. So this is the first port, this is the second port. Like what I mentioned earlier on, when we actually design by using image parameter, we need to specify the pass band and the stop band. This is for a low pass filter. So over here, you can see that this part will be pass, this part will be stop. This is for high pass filter. So at low frequency, this will stop. And at high frequency, this will be pass. Okay, so basically, we are going to adopt this image parameter to design low pass filter. This diagram here shows the cascading of different function of filter design. Let's come to this constant K first. This constant K actually specifies the pass band and stop band. So in short, this constant K will develop whether it is a low pass filter or a high pass filter. Next will be this m-Derived. The typical function of this m-Derived is to develop a sharper roll-off factor. With this session, you can actually design a pole at whatever frequency. With this, you can imagine that you are going to achieve a better cutoff frequency. Next, this is a filter design. So you can see that at the outer stage, you can see that this is actually mainly for matching session. So when M is equal to 0.6, this is ideal for matching impedance network. Let me kickstart the design rule of constant K filter design. So basically, this will be the stages to design a constant K. Like I mentioned earlier on, typically is to determine whether it is a low pass or high pass filter. So this diagram here shows the low pass filter. You can configure them as T or a pi form. So this is actually for the T form. This is actually for the pi session. The equation to compute this will be the radian C. It is equals to 2 pi fc. So this is 2 over divided by square root LC. This LC will be the design for this low pass filter. In order to find the value of L, you can actually adopt this equation. Same for C. Another set of equation can help you to determine the C value. So therefore from here, you can easily design the L and the C value. This is for low pass filter. We also have the high pass filter. But for this video, I mainly will concentrate on the low pass filter. Next, let me explain the design rule of m-Derived filter session. This is for low pass filter. This is for high pass filter. Like I explained earlier on, okay, this method m-Derived is to achieve a pole at a certain frequency. So basically, this will be the frequency that you want to position the pole. With strategized position of the pole, you are able to achieve a sharper cutoff frequency. So this is desired from the m-Derived session. How to get the L and the C value? basically will be from the same constant K method. How you compute the L and C for this constant K filter design, you can actually adopt into this m-Derived filter design. So from here, you can see that based on the prediction of the pole at certain frequency, you are able to achieve a m value. But for matching, like I explained earlier on, typically for m need to be at 0.6. For matching, I need to break them into input and output. So from here, you can see that this is for low pass filter, this is for high pass filter. Like I mentioned earlier on, I need to separate the input and the output. Again, the L and C method can be derived from the same constant K method to calculate the L and the C value. After that, you can actually put them into this to obtain the design of the matching session. Before I continue, guys, this is very important for me. I hope you can help me by like this video. Guys, it's free. Help me. Press the like button now. For those who are new to this channel, please help me by consider to subscribe to this channel and turn on your notification bell. Once again, thank you so much for strong support. Let's come to the working example of image parameter filter design. This example, we are tasked to design a low-pass composite filter with a cutoff frequency of 2 MHz and the impedance of 75 ohm. Okay, so basically, the impedance need to be achieved at 75 ohm. We also need to strategize placing an infinite attenuation pole at 2.05 MHz. So this will be the design of composite filter. Because we need to achieve a sharper cutoff, so therefore we have this m-Derived state. However, okay, I must emphasize this, we can in fact omit away this if we can sacrifice the sharper cutoff. If let's say the design, we don't have the stringent of having a attenuation pole at 2.05 MHz, then we can actually omit this stage of design. So from here, you can see that typically we just have the M session, okay, and then with this constant K, we can actually so-called omit away this m-Derived. But with this example here, we are tasked to design an attenuation pole at 2.05 MHz. Hence, we need to have this m-Derived in order to achieve a sharper cutoff frequency. Let's kick start by concentrate on the constant K method first. Let's come to the design of constant K. Okay, so this is what I showed it to you early on. This is for low pass filter. How to compute the L and C will be with this formula. So once we know the R naught, which is 75 ohm, this is WC, which is equals to 2 pi FC. Okay, so basically the FC will be equals to 2 MHz. So from here, we can easily compute the L and also the C value. Because this is L divided by 2, so this is L, so I need to do a divide by 2. So therefore, the inductor value will be equals to 5.97 microhenry. Since these two are the same, so basically the C value will be remain the same, which is 2122 picofarad, as you can see from here. So this is how we design the constant K. So with this, okay, we can easily replace this part under the constant K. So next, let's concentrate on this m-Derived filter design. Let me explain the design rule of m-Derived T session. This is what I have explained early on. Remember, we need to put a pole at a strategized position in order to achieve a sharper cutoff frequency. This is from the design of this low-pass filter. If you still remember, we can compute the M value. This FC will be the cutoff frequency at 2 MHz, while the pole need to be at 2.05. So basically with this, we can work up the number of M, which is 0.2195. Next, okay, we need to compute all this value. If you still remember, the L value, this is what we actually calculate early on. Okay, so basically we calculate this L value using the constant K method. After that, we can actually use back the same L and C value in this equation to compute the m-Derived so-called session. Okay, basically from here, you can see that I have successfully compute this inductor value, which is 1.310 microhenry. I have also successfully compute this capacitor value, the MC. Okay, so basically from here, I just need to take this 0.2195 multiplied by the C value. This will be the capacitor value for this MC. Next, this inductor value, as you can see from here, I can also easily compute. So once I'm done with this, I can actually draw this m-Derived T session. Okay, so basically this ml over 2 will be 1.310 microhenry. Okay, so this MC value will be at 465.8 picofarad. Next will be this inductor value will be equals to 12.94 microhenry. So basically with this, we have successfully designed the m-Derived T session. Okay, so basically this will be represent this m-Derived T session over here. So next, we need to focus on the matching session. This is the design rule for matching session. If you're still able to recall, I mentioned that the m value need to be at 0.6 in order to achieve the matching session. This is for low pass filter. You can see that this is for input and this is for the output. Basically, I can easily compute the component value as you can see from here. With this, I have successfully designed the matching component for the input and also the matching component at the output. And if we put all this at the input and the output, I have successfully designed this low pass composite filter with a cutoff frequency at 2 MHz, and I also strategized put this attenuation pole at 2.05 MHz. And therefore, like I mentioned earlier on, I can put all these stages into one. One thing I like to highlight, we can actually combine these two inductor value so that it is much more easier for us to understand. This will be my last slide for this video. Okay, so this diagram here show the frequency response from 0 to 4 MHz. This is for low pass filter. So therefore from here, you can see that this is actually the S12 diagram. You can see that from low frequency, every component will be able to pass. The first pole will be because of this strategized location of 2.05. So basically, this is actually due to m is equal to 0.2195. Then we are able to achieve this strategized so-called pole with the m-Derived filter session. Next, another pole is in fact due to the matching network, which is m equals to 0.6 session. With this, I'd like to end my discussion. If you have learned something from this video, urge you to help me by like this video and subscribe to this channel. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.